In this short video, we're going to go over the trapezoid rule because this is fair game on the Calc AP test. There are some elementary functions that do not have antiderivatives that are elementary functions. For example, there are no elementary function that has the following function as its derivative. So here's x to the third, or the cube root of x times quantity 1 minus x square rooted, the square root of x times the cos of x, or cos of x over x, square root of 1 minus x cubed, or the sine of x squared. To find an antiderivative, that would be tricky work, or sometimes even impossible. So if you need to evaluate a definite integral involving a function whose antiderivative cannot be found, then while the fundamental theorem of calculus is still true, it cannot be easily applied. In this case, it's easier to resort to an approximation technique. And two of those techniques are described in this section. We're just going to talk about the trapezoid rule, not the Simpson rule. And we've done these similar things to this before with the midpoint rule or the left and right hand sums of rectangles when we first started exploring the area under a curve. So one way to approximate the definite integral is to use some number n of trapezoids, as shown over here in the figure. In the development of this method, assume that f is continuous and positive on the interval from a to b, such that this definite integral from a to b represents the region bounded by the graph of x, the graph of f, the x-axis, and the lines x equals a and b. And I'm going to stray away from what the book has here. This is the formation of the trapezoid rule and letting the limit of n go to infinity and all that. If you're going to see this on the AP test, it's probably going to be just a strict partition, something small like 4, 5, or 6 trapezoids. So let's take a look here. We got this area under a curve, and we're going from A here at x sub 0 all the way to x sub 4 at B. So we are chopping that area up into 4 rectangles. And notice, we have here is x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. And we follow that up until we hit the function. At each of those, we have those heights of each of those. And then we connect those heights to form trapezoids. So we connect through here, and we're under the curve a little bit, but here then we go over the curve, and we have these 4 trapezoids. Okay, now it's easier to see if I give this a rotation. Oh, I guess I got everything on there. I guess that didn't work as well as I was hoping. The formula for the area of a trapezoid is 1/2 the height times the sum of the bases. Oops. 1/2 the height, 1/2 height, times the quantity base 1 plus base 2, the sum of 2 consecutive bases. Now let's look here on these trapezoids. I'll make the top one here. This side is the first base of the top trapezoid, and then this would be the bottom of that same trapezoid. But the bottom of, well, let me label these 1, 2, 3, and 4. So trapezoid 1, the red line is its the top base, and that is x sub 0. And the bottom of trapezoid 1 is the blue base, and that's x sub 1. And that x sub 1 is the bottom of trapezoid 1. It is also the top base of trapezoid 2. And then we have here at x sub 2, this blue line will be the bottom of trapezoid 2, and that line also happens to be the top of trapezoid 3. So let me do this. When we do this, it is going to be a summation of trapezoids. So we're going to have our 1/2 height times the sum of the base, base plus base. Okay, now down here I have the summation of, we're going to have 4 trapezoids. Here's trapezoid 1 plus trapezoid 2 plus trapezoid 3 plus the last trapezoid. And notice the formula is the same for all of those. 1/2 the height times the sum of the bases. And for those bases, I'm going to use x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So this will be 0 plus 1 The next one will be 1 plus 2, and then we'll have 2 plus 3, and 3 plus 4. Again, because we do have that overlap, this base 3 is the bottom of one trapezoid while it's the top of the next trapezoid. And now let's think here, what can we factor out in front of the summation? The 1/2 is common to all the trapezoids, so we can pull the half out front. And we also have the height of the trapezoid, and let's start thinking about our notation. The height of the trapezoid is our delta x, or how wide is each of these trapezoids. So that's our delta x. So I'll write that in there, delta x. And then what we're left with is base sub 0 plus base sub 1 plus base sub 1 plus base sub 2. And let me write it like this. We start out with 1 base sub 0, the first base, and then add to that. Here we have a b sub 1 and another b sub 1, so we have 2 of those b sub 1s. And then we have b sub 2 and another b sub 2, so we have 2 of those. And then b sub 3 and another b sub 3, so we also have 2 of those bases. And the last one here, b sub 4, we only have 1 of those. 1 b sub 4. So notice here there's a little pattern. We have an implied 1 here. 1, 2, 2, 2, 1. The bookends are 1s. Everything else in the middle is 2. Again, because of that overlap between the bases. So to find this trapezoidal approximation, we're going to have a half out front. Whatever our delta x is, the width of our partition, we'll multiply that by. And then we just sum up those bases. And you know, with the function notation, that would be f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2, and so on back to the final over here where we only have 1 of those. So as opposed to memorizing the formula, I think it's kind of easier just to work your way through it. If you just remember the formula for a trapezoid's area, half the height times the sum of the bases. The height, when you rotate the graph 90 degrees, the height is just delta x, so you factor that out, factor out the half, and then you sum up the bases. You're going to start with 1 of these, and then you're going to have 2 of everything in the middle, and then 1 at the end of that last base. And again, if you do see something like this on the AP test, it might be a free response or a multiple choice you got to do some scratch work on. But what they're probably going to do is give you a partition of 4 or 5 or 6 trapezoids. So here's the theorem for that. Again, this is more the calculus notation of it. Let f be continuous on the interval from a to b. The trapezoid rule for approximating the definite integral from a to b of f of x dx is given by, and there's our definite integral. F of x dx is approximately b minus a over 2n. Remember, b minus a is how we find the width of each partition of each delta x. That's the endpoints, b minus a divided by the number of n trapezoids we want to cut this up into. And the 2 down there comes from the 1/2. So again, this is our delta x. The 1/2 is built into the trapezoid formula. And then here we have the sum of the bases. 1, f of the first piece, x sub 0, and then we have 2 of the next, and 2 of the next, dot, dot, dot. 2 of the second to last, and then we have 1 on the end again. And then, you know, here's where you actually do the calculus. You let n go to infinity. The right-hand side approaches the exact value of the definite integral. And they do make sure, again, observe the coefficients in that trapezoid rule have a 1, 2, 2, 2. Everything in the middle has a 2 in front of it. And then you get to the right endpoint, and that is also 1. Let's check out example 1 here. And it says, use the trapezoid rule to approximate the definite integral from 0 to pi of sine x dx. And compare the results for n equals 4 and n is 8. And let's just do the n as 4. And then I got, this is a trig example, I got an algebraic one on the next slide. And this is something we could do with the fundamental theorem of calculus because we know the antiderivative of sine. But again, we're doing this for the estimation technique. So let's see here. I'm sort of just going to rotate this. You know, this is sine from 0 to pi is in the first quadrant. You know, we have that first bump in the first quadrant. Sine goes through the origin and crosses that pi. So we want to find that area from 0 to pi by chopping it up into 4 subintervals. So our delta x is b minus a over n, and our b is pi, a is 0, n is 4. So we get pi minus 0 over 4, which is a quarter pi, will be the width of each subinterval. So here is 0 to pi, and we got it chopped up 1/4, 1/2, 3/4, and then 1 pi. Again, you can really see the trapezoids. We'll give this a little rotation here, 90 degrees clockwise. And our first one, you know, here's just a little tiny speck for the top base. And then here's the bottom base. And this bottom base is also the top base of the second rectangle, or trapezoid. Let me label these 1, 2, 3, 4. And then here will be our next base, and another one, and then our last dot at pi. So let's see. We're going to have a summation of 4 of these trapezoids, and the trapezoid formula is 1/2 times the height times the sum of the bases. And remember, the half is a number. We can factor that out, 1/2. The height of each trapezoid here again is our delta x. That's going to be a pi over 4. Pi over 4. And then we will have the sum of bases. Now don't forget, it's b1 plus b2. And then we go b2 plus b3. And then another b3 plus b4. So is that all of them? No, I'm missing that 1, 2, 2, 3, 3, 4, and 4, 5. Again, we have 4 rectangles, but you know, here is 1, 2, 3, 4, 5 places that we are evaluating the function at. So everything in the middle, we have doubles of those. So we're going to have our 1/2 and then our delta x, and our first base is going to be the sine of 0, you know, when we evaluate the function here at the origin. And then we're going to have plus 2 times the sine of pi over 4. That's sine pi over 4. Plus 2 times the sine of the next one, pi over 2. Plus 2 sine 3 pi over 4. And I'm running out of room. Plus 1 sine of pi. Again, at the endpoints, we just have 1s. 1 at the start, 1 at the end. Everything else in the middle is doubled because of the overlap of the bases. So outside the brackets, 1/2 times 1/4 pi is pi over 8. And then what do we have in the brackets? Sine of 0 is 0, so that's nothing. And then we're going to have 2 times the sine of pi over 4. And the sine of pi over 4 is the square root of 2 over 2. Plus 2 times the sine of 1/2 pi is 1. And then we're going to have 2 times the sine of 3/4 pi. And that is again a square root of 2 over 2. And at the end, a plus 1 times the sine of pi, and that's 0. So we don't need that there. We can close that off. So there are the mechanics of, you know, cutting that up into 4 trapezoids underneath the sine wave. And let's see what we have here. This 2 divided by 2, that will cancel, as it will here. So we're going to have the pi over 8 outside. And then we're going to have a square root of 2 plus 2 plus another square root of 2. So that's 2 plus 2 roots of 2. If you notice the screen change there, I did have some technical difficulties, and I just got to redo part of this video. We got down to this answer, pi over 8 times the quantity 2 plus 2 roots of 2. And on the AP test, make sure to read the directions carefully. Usually if you had to do something like this in a free response question, they would ask you to round the answer off to like 2, 3, maybe 4 decimal places. So this is something you'd want to punch into your calculator, possibly, and get the decimal approximation. And that's about 1.974. Again, this is something you could do with the fundamental theorem of calculus, but on the test they might specifically ask for the trapezoid rule approximation. You could always check your answer by definite integration. All right, now here is a algebraic example. We're going to find the approximation of the area under the curve from 0 to 2 of x squared dx, chopping that into 4 subintervals. So we're going to go out to 2. That'll take us to a height of 4 on the y-axis. Since we have the squaring function, it'll look something like this. Let's see, n is 4. We're going from 0 to 2. So to find our delta x, or in this case the height of each trapezoid, that'll be b minus a over n, or 2/4 or 1/2. So again, always remember we're doing this is a summation of trapezoids. Half the height times the sum of all the bases. So the half is just part of the equation. Our height here, or delta x, is also a half. And then we are going to do a sum of all the bases, starting with the first one, doubling all the ones in the middle, and then taking the last one, because remember that overlap. So if we're chopping from 0 to 2 up into 4 subintervals, it's going to go by halves. So we're going to have a 1/2, and then 1, and then 1.5 or 3/2, and then 2. There are our 4 subintervals. Okay, so we take 1 times the first one. So we're going to do f of 0, and remember our function here is x squared. So that goes in, 0 squared is 0. Plus, we're going to have 2 of these, and we throw that into the squaring function. Half squared is a 4th. Plus, we'll have 2 of these. Throw the 1 in, 1 squared is 1. Plus, we're going to have 2 of these. Throw in the 3/2 and square it, and you get 9/4. And then we throw the end point in. Remember, we only do 1 of these. We do 1 on the end here and 1 over here. 2 squared is 4, and that's times 1. 1 times 4 is 4. And I drew into my graph a little bit, but that's okay. Here, we'll have a half, and a half is a 4th. And now all of our heights summed up. 1 times 0 is nothing. 2 times a 4th is 2/4 or a half. Plus 2. Plus 9/4 times 2 is 18/4. That will reduce to 9/2. And then we'll have a plus 4. That's a little better. So let's see here. We're going to have a 4th of, let's convert everything into half. Well, if we add these together, 1/2 and 9/2 would be 10/2, and 10/2 reduces to 5. And then we'll have 5 plus 2 is 7, plus 4 is 11. 11 times 1/4 is 11/4. Or again, they might be asking on the AP test for the decimal rounded off. And in this case, it's not going to be rounded. It's going to be perfect. Because if we divide that in, that'd be what, 2 3/4, or 2.75 is our approximation. Again, especially if this is on a free response part or even on a multiple choice, draw yourself a little picture. And remember, you are finding rectangles. So our first rectangle, we just connected those endpoints with a straight line segment. And then we went up to the next one, connected that straight line segment. And that would also help you remember to double these inner ones here, because the base of one trapezoid, the bottom base of one trapezoid is the top base of the next. And again, we're connecting these in there. And you could always check your work with definite integration.